it's not polar.
It's not polar.
Or is it? I don't think it is.
Okay,
Is it the exception?
there's only one way to find out. How about we start with the rule? Okay, so the question is asking, they want us to use the information that we have, use the information that we have for them on the table, and we need to provide reason as to why BH3 does not dissolve in water. And this is the table. We need to give reason why it does not dissolve in water. And I'll definitely try and take this step by step, okay? You understand?
Yes.
Okay. So you know what I'm going to do? The first thing, let me talk about the rule. Okay? So I'm going to first talk about the rule. Remember that uh, like dissolves like, ne? Do you know this?
Life dissolves.
Look at this.
Sorry. Like dissolves like, okay.
And then another rule that I can give you is that the polar substance, the polar substances, they will dissolve. Okay, we are saying that the polar substance, they dissolve in polar substance. Are you following?
Yes.
Okay, I think we're going to work well in chemistry. I see that you understand this one. So another rule is that the non-polar,
Dissolves non-polar. But
exactly,
water is polar, so would that not make BH3 non-polar?
it will make
BH3 non-polar.
BH3 non-polar.
If water is polar and it's not dissolving in water.
Exactly, that's correct. That's correct. So a non-polar substance dissolves in non-polar. You know why I'm teaching you like this?
Yes.
Because I want you to be the best.
Thank you.
Right. I want you to be the best. I don't want you when you answer question, you do guesswork where you don't understand where is that question coming from. So
Yeah.
when I look at this, they are asking us to give a reason using the information about solubility given in the table, provide a reason why BH3 does not dissolve in water. Let's first talk about the water. So if you look at the water, so the water is polar. Do you agree with me on that?
Yes.
So the water is polar, and then the BH3. If you still remember, we just talked about this BH3, and we said that the BH3, we said this is trigonal plan. Okay, so now, and we also said that it's what? The BH3, it's also symmetrical. You still remember that?
Yes.
Okay. And we also talk about the BH3 being bond dipoles cancels. Okay. And then we also talk about the BH3. We said that this BH3 is what we call it's non-polar. You understand? So this tells you that by this we can definitely say that the BH3 does not dissolve in water, and what's the reason for that? So it does not dissolve in
Because
water because this BH3 is non-polar while water is polar. Because BH3. The BH3 is, we said this is non-polar, but water is polar. The water is polar, so there's no way that BH3 will dissolve in water. Are you happy about that?
Yes.
But before we move to the next question, I still feel like I need to make sure that this sticks in. What I need
Don't
to tell you is that,
don't
oh, you have a
don't
question.
much. I'm very good with chemistry. I very much understand.
Okay, remember polar plus polar is equal to dissolves,
So,
né?
yes.
And then non-polar plus non-polar, this is equals to what? Dissolves. And then what about polar plus non-polar?
Polar, it doesn't dissolve.
Exactly. Does not dissolve. Okay,
Yes.
let me move to the next question. 1.7, I'm very sorry. So briefly explain the difference in boiling points for each molecule. Be sure to use the concept of intermolecular forces and the energy to explain your answer. So they want us to use explain the difference in boiling points of each molecule. So we can see that the BH3 has minus 92, the ammonia has minus 33.35. Be sure to use the concept of intermolecular forces. The intermolecular forces. Okay. So if we are using the intermolecular forces, I'll definitely start by writing down and say my BH3. This is 1.7. The BH3, it has the boiling point of negative 92 degrees. And then the ammonia NH3, this one has a boiling point of negative 33.35 degrees. So look at this. Tell me which one has the highest boiling point.
Um. Ammonia.
Exactly. So the ammonia, this guy
That means
has
a stronger bond and hydrogen, because hydrogen bonds are stronger and London forces are not as strong.
say that again.
Um, the ammonia has a higher boiling point because it's a hydrogen bond, and hydrogen bonds are stronger than the London forces, so that's why the boiling point is higher. No.
Exactly. Wow. That's you look at this, ne? You see the BH3. So if we analyze this thing step by step, the BH3, ne? You see the BH3. So what I can say about the BH3, I know that the BH3, this guy is a non-polar molecule, right?
Yes.
Polar molecule. And then the BH3, it will have only what? London forces. Wow. And then it's weak. Okay? And then the NH3, this one is a polar molecule. And then we're going to say it has dipole
Dipole.
forces, né?
Yes.
And also it also have what? Hydrogen bonds, né?
Bond.
So it also have hydrogen bonds. And then this one, we can say it's very strong. The NH3 is very strong. Right. So when I look at this, I'm just going to give you the answer now. Né? By using the intermolecular forces, I'll put my answer like this. But before I give you the answer, remember, the stronger the intermolecular forces required, more energy to overcome. Okay?
Yes, which is why they have higher boiling points, because their bonds are stronger, so therefore there's more energy required that goes in to breaking them, also to create a hydrostatic no, what's this thing, am I not hydrostatic, what's this thing with the EMF graphs and stuff.
Exactly.
Yeah.
I definitely get what you are trying to say, and that's very correct. You know, like I just wish if
And endo exothermic reaction.
exactly. You know, just to say this, né? You really remind me when I was still in school. I used to master like trigonometry. I used to master stoichiometry and also chemistry. The stoichiometry I know is also part of chemistry, but
And
you
it's
see
so
you see now when you go to grade 12, there's this one. They say Lee-Chatelet's principle, where you have to give like it has to do with theory, intermolecular forces. You understand? I used to master those topics, especially rates of reactions.
yes, it's easy.
Yeah, they are very easy. So we say that the NH3 molecule, they form the hydrogen bonds. Because
Which was,
now, you know why I'm writing this down? I'm
yes,
trying to train you also how to put your answer. So the NH3 molecule, they form a hydrogen bond, which are, we say that the
strong,
hydrogen bond which are stronger.
strong
So they are
than the
stronger than what? They are stronger than the
BH3
London
line.
forces. Right. So between, they are stronger than the London forces between the BH3 molecule. Then now you can talk about the energy. This tells you that more energy is required to overcome the intermolecular forces. You still with me?
Yes.
The intermolecular forces in NH3. Okay, so therefore, the NH3 has a higher boiling point than that BH3. Can we move to the next question? I think this we're
Let
done
me
for
just
question one.
write
Eh?
it down. Let me just, okay.
Question two. The table below, you still with me?
Yes.
The table below shows the boiling points of the hydrides of group. Is this group 5?
Wait, I think so.
And then in which hydrogen is bonded to elements from group 5 in the periodic table. They say boiling points of hydrides from in group 5. We can see that. And then hydrides of group 5, this is CH4C. Okay, I can see that. And we have the relative molecular mass for each of them. And then we have the boiling point. You know?
Yes.
Okay, differentiate between intra-atomic force and intermolecular forces using CH4 as an example in your explanation. Okay?
Yes.
Okay, so I'm just gonna try to make this one short. This question too, I want us to kill it fast. Okay?
Okay.
They say we need to, let me go back, differentiate between the intra-atomic forces and intermolecular forces using the CH4 as an example. Okay, you know what I'm going to do first? This is where I'm going to start. First thing first, I'm going to talk about the, the force inside a molecule. Né? So I'm going to first talk about that intermolecular forces.
Yes. It's a molecule. It's the force within a molecule that holds atoms together.
Exactly. So now, the not the intramolecular forces. Né?
Or between the molecules.
Yes.
Okay.
So this will be, let's talk about the intramolecular forces. So for this one, these are the forces inside the molecule, okay?
Okay.
Right. So if these are the forces inside a molecule, we can say that, remember, this force, they hold atoms together, okay?
Yes.
They hold atoms together. And then one example, maybe the example that I can give you is the CH. If you look at the CH bond in what? So the CH bond in that CH4. So that's the example. So these are covalent bond. We call them the covalent bond, okay?
Okay.
Right. And then now that you understand about the intra, let's talk about the intermolecular forces this time. Okay?
Yes.
So the intermolecular forces. So the intermolecular forces, these are the forces between what? These are the forces between molecules. And then since there are forces between the molecules, maybe I can give you an example. When we say between molecules, this is the attraction. Remember, I'm giving you an answer. Eh? So this is the attraction between one CH4 molecule and another CH molecules. Ne? And we know, what do we call those forces? The London forces. Are you happy with that?
Yes.
Okay. So to answer this, to answer your question, you're going to say the the intramolecular forces, they are covalent bonds. Okay?
Yes.
And they are holding, since they are covalent bonds, we're gonna say they are holding what? Atoms together.
Yes.
Right. They are holding atoms together within that CH4. And then within the CH4 molecule. And then while the intermolecular forces, these are the attractive forces. So they are the attractive forces between the neighboring what? The neighboring CH4. Are you still with me on that?
Yes.
And that's your answer. So the intermolecular forces are the covalent bond holding the atoms together in that CH4. And then the intermolecular forces, they will be
Okay.
the attractive forces attractive forces between the neighboring CH4. Can we move to the next question? Do you understand how to answer this one?
Yes. Wait, pardon. Please repeat yourself.
Is it?
Please repeat yourself.
Okay. We are saying that, look at the statement that I'm saying, that I'm reading from there.
Yes.
First thing first, we are saying that the intramolecular forces are the covalent bonds holding atoms together. Ne? And then
Yes.
you still with me?
Yes. I'm just confused. Are we on 2.2?
No, 2.1.
Yo, still okay.
I'm sorry. You want to move now?
Yes, I didn't
Let
know
me
that.
move to 2.2. What is the phase, solid, liquid, or gas of the hydrides above at 25? Ne? So
Yeah.
I'm just going to quickly move on this one. Remember, I always like to talk about the rules. Ne? If the
Mm,
boiling point is below 25 degrees, the substance exists at what? Gas at room temperature. Ne? So
Yes.
all hydrants shown in this diagram, let's look at them. If you can look at all this gas, they have a boiling point that is below the room temperature. So the answer is that when they say what is the solid, what is the phase, the answer is that all of them, they are gas. Remember, you check what? We check the boiling point. If the boiling point is below 25 degrees, then you can definitely say that uh, if the boiling point is less than 25 degrees, it's a gas. So all of them are gas. Can I move to 2.3?
Yes, and
Wow,
the
is that how you want me to teach?
it's non-polar.
Eh?
No, it's just that I understand chemistry, so it's not really, this is just a bit of revision, jogging my memory.
Oh, okay, nice. And then what is the polarity of molecules of hydrides? What is the polarity?
Uh,
Hydrides.
is it hydrogen bonds?
No, the polarity. And now, if you look at
Oh,
this, né?
because when you look at it, it's hydrides of group 5, which have the tetrahedral shape, which is symmetrical, and then if it's symmetrical, then the dipoles cross out, making it non-polar.
Let's talk about this one. CH4, né? I totally agree with you. You said this one is a tetra, né?
Yes.
Okay? And then now we said that it's symmetrical, né?
Yes.
And then another thing, it's a bond. The bond is dipole. We said the dipoles cancel, né?
Yes.
And then therefore is going to be what? A non-polar.
Yes.
So same applies to all of this. Same applies to all of those three. All of them, they are non-polar. Do you understand?
Yes.
Okay. 2.4. Name the type of van der Waals forces between molecules of the hydrides in the table above.
London forces.
Exactly. London forces. Okay, so why are we saying they are London forces? Because we said all of them, they are non-polar. So non-polar, they experience the London forces, okay?
Yes.
This is how you want me to teach, ne?
For now, yes, just because it's not that I don't
Okay.
understand.
So, and then they say that explain the trend in the boiling point observed for the hydrides in the above table. In your explanation, refer to the molecular size, intermolecular force, and the energy needed. Okay. So when they want you to explain the trend in the bonds observed for the hydrides in the above table, so they want us to talk about, we need to refer to the molecular size, the intermolecular forces, and the energy needed. Why we don't even have mark allocations yet?
I'm not sure.
Okay, let's look at this. What do you observe about the boiling points?
They're relatively low.
They, let's say the boiling point increased down the group. Will you understand when I say the boiling point increased down the group? Then I'll
Yes.
explain why.
Okay.
Okay, so we are saying that it's moving down the group. If it's moving down the group, what can we say about the molecules? The molecules becomes larger,
Oh,
né?
okay.
Meaning that there will be more electrons, okay?
Yes.
And then there are more electrons, then electrons clouds, they become more easy to distort, and then temporarily the dipoles, they become stronger. And then now what can we say about the London forces? The London forces increase.
Okay.
Since the London forces increase, more energy is required to separate the molecules. Therefore, the boiling point increase. So let's go to the question and answer this. Explain the trend in the boiling point. So we are saying that as the molecular size increase down the group. So as it increases down the group, the number of electrons, we're going to say the number of electrons increases. Do you understand that part? Are you still with me?
Yes, sorry.
And this will do what? This causes this will cause the stronger London distension force between what? I need you to pay attention between molecules.
Yes.
And then what can we say about the energy? So more energy.
More kinetic energy is required.
Exactly. More energy is needed. More energy is needed to overcome this molecule. 100%. And then now, therefore, the boiling point increases. Therefore, the boiling point, it will increase. And then it increases where? Down the group. Are you happy with this answer?
Yes.
Do we still have time? Let me check.
Yes.
Oh, we still have time. Let's push to question 3 now. Is this the last question?
Yes.
Wow, there's still question
No,
4. What?
it's not the last question. I still have until.
What?
But I'll do them. Fine.
Okay, let's move to question 3. Question 3 says the graph below shows the points of hydrides of group 5 in the periodic table. We can see that draw the Lewis structure for H2S molecule.
So
the
you're gonna
H2S molecule, that's, what is this? It's sulfur and hydrogen, eh?
Yes, you're gonna put the S in the middle, and then you're gonna draw the two lines to show the bonding pairs, and then you're gonna indicate the lone pairs as well.
The low pairs as well. That's what I was looking for, né? So we're going to say that the sulfur has 6 valence electrons, right? So we put the bonds like this, right? And then we're gonna say the 2 atoms of they contribute 2 electrons. So I'm just gonna, should I put them, maybe should I put them somewhere here on top of, should I put them on top of sulfur?
Yes, you put 2 dots on top of S, 2 dots below the S as well.
Right, because sulfur has 2 lone pairs. So what you need to do, you need to always show the lone pairs, okay?
Yes.
Okay, 3.2. From the graph above, they want you to deduce and then write down the name of the hydride. Okay, so you know to do this, you need to look your lowest boiling point. Therefore, when they say, okay.
It's H2, it's the H2S.
Is the H2S?
Yes.
Okay. Okay, so with the weakest intermolecular force, what's going on this 3.2? I don't understand what's going on, because I'm trying to read the question and the question is not making sense.
Refer to intermolecular forces and energy.
Oh, this question is for 3.2, because now when I read 3.2, now this makes sense. Now it's for 3.2.1, because in 3.2.1, they say from the graph deduce, then write down the name of the hydride with the weakest intermolecular forces. Yes. The one that is the weakest is this one, because this is the one with this boiling point here. So it's H2S. So this is just gonna go there. You see how I trust you? I'm already writing the H2S here. And that was not even the complete question. 3.2.3, with the hydrogen bond between molecules. So when they say the hydrogen bond between molecules, remember the hydrogen bonding occurs only when H is bonded to F, the fluorine, O, the oxygen, and N. And now, when we look at this, we know that the water is the one that contains the OH bond in it. So the correct answer will be water. Are you still with me, or are you sleeping?
Yes, I'm still listening.
Yeah, so this is H2, H2O. The water is the one that is bonding with the OH. So for 2.3.2, that requires the most energy to undergo a phase change. So the trend, if you look at this now, when they say the one that requires the most energy is the one with the highest boiling point, okay? I'll go on the graph and look at the one with the highest boiling point. I want to see if you can manage to get this one. Which one has the highest boiling point?
H2O.
Are you sure it's H2O? Highest
Yes.
boiling point on the graph.
Yes.
Tell me, if I have, look at this. Go back from the graph above, deduce, then write down the name of the hydride that requires the most energy to undergo a phase change.
H2TE, then if it's not H2O.
Exactly, the H2T. Nice. Okay, so now refer to the intermolecular forces and the energy and give a reason why of the hydrides group divides from the trend in the boiling point and observed for others. So let's talk about the trend. Né? So the trend, and normally boiling point increase with molecular mass. Do you know that?
Yes.
The boiling point, it increase with molecular mass.
Okay.
Right. And then when I look at the exception, and then the exception here will be water. Why? Because water forms hydrogen bond. Okay, the water, it forms the hydrogen
Bond.
exactly. Okay, and then the hydrogen bond, we know that they are much stronger than the normal dipole or London forces. Okay, so this tells you that extra energy is needed to break them. Né? So what can we say about water? So water has much higher boiling point than expected, okay? So do you want me to write down the full explanation?
No, it's okay.
You sure?
Yeah.
Or maybe, okay, it's fine. Do you want us to stop here?
Yeah, that should be fine. Thank you.
You sure?
Yes.
Okay, so I think that's it for today. Né? I think I'm very happy with the level of your understanding on chemistry. I am very happy because I saw when we were working on that other side. I think you really understand this. Né?
Yes, it's so easy.
Yeah, né? Thank you very much. Can you please have a great evening? And I'll definitely see you on our upcoming lessons. Né?
You too. Thank you.
Thanks. Bye.
I Yeah. How do I go now?